Assalamualaikum and good morning to all students. So last week we have learned about fluid properties. Now we dive in more in fluid statics. We will learn about pressure and manometer. As you can recall, in statics, pressure is defined as a normal force exerted by a fluid per unit area. We speak of pressure only when we deal with a gas or a liquid. Pressure is always used on solid surfaces, which is similar to normal stress, or the force acting perpendicular to the surface per unit area. Since pressure is defined as force per unit area, the unit is newtons per square meter. It is also known as Pascal. The pressure unit Pascal is too small for most pressure measurement. Therefore, we always use in megas or kilopascals. Bar standard atmosphere and kilogram force per square centimeter are the other pressure units that are commonly used in practice. If you try to hammer a bowling pin into the wall, nothing would probably happen. However, if you hammer with the same force on a nail, the nail would be a lot more likely to penetrate the wall. This shows that sometimes just knowing the magnitude of the force isn't enough. You also have to know how the force is distributed on the surface area of the impact. For the nail, all the force between the wall and the nail was concentrated into the very small area on the sharp tip of the nail. That is why the nail can be easily penetrate the wall. However, for the bowling pin, the area that is touching the wall was much larger, and therefore the force was less concentrated. So first, let's talk about the atmospheric pressure. There are three types of pressure: absolute pressure, gauge pressure, and also vacuum pressure. The actual pressure at a given position is called as absolute pressure. For absolute pressure, the point of reference is the perfect vacuum. This point has been chosen because it is the lowest possible pressure. In particular, there is no pressure at all. A perfect vacuum would mean that all particles have been removed from a closed volume. In this volume, which is then completely empty, pressure cannot be present. As already said, absolute pressure is always a positive number. Negative numbers are impossible because there is no pressure below the perfect vacuum. Most pressure measuring devices, however, are calibrated to read zero in the atmosphere, even though there is actually pressure exerted upon it. And so, they show the difference between the absolute pressure and the local atmospheric pressure. So this difference is called as gauge pressure. Gauge pressure can be positive or negative, but pressure below atmospheric pressure are sometimes called vacuum pressures, and they are measured by a vacuum gauge that indicate the difference between the atmospheric pressure and the absolute pressure. A solid surface can exert pressure, but fluids can also exert pressure. Let's say you put your leg into a swimming pool and you can feel the force that pressing your legs. So this is the pressure due to the liquids. Imagine being submerged to some depth in water. The water above you would be pushing down on you because the force of gravity and would therefore be exerting pressure on you. If you go deeper, there will be more water above you, so the weight and the pressure from the water would increase too. That is why a deep sea diver needs to wear special suit and equipment in order to withstand the high pressure within the deep sea. Let's take a look about pressure at a point. Pressure is the compressive force per unit area. So we might think it as a vector. However, pressure at any point in a fluid is the same in all directions, so it has magnitude but not a specific direction, and thus we can consider it as a scalar quantity. So this can be demonstrated by considering a small wedge-shaped fluid element in equilibrium, as shown in this figure. The mean pressures at three surfaces are P1, P2 and P3, and the force acting on the surface is the product of mean pressure and the surface area. Force equals to pressure times area. From Newton's second law, a force balance in x and z direction. In z direction, we have to consider the weight of the element, so W equals to mass times gravity. Noting that the wedge is right triangle, so we have delta x equals to L cosine theta and delta z equals to L times sine theta. Substituting these geometric relations and dividing by delta y and delta z, we will get this equation. The last term will drops out as delta z close to 0 and the wedge becomes infinitesimal, and thus the fluid element shrinks to a point. Then combining the results of these two relations give P1 equals to P2 equals to P3. So we can conclude that the pressure at a point in a fluid has the same magnitude in all directions. So now let us consider the total y component forces in a small element in the fluid. Since the element is in equilibrium, the total x component force is equal to 0. We can consider that The area for the upper and the below surface of the element is the same. Just like we learned in previous slide, force equals to the pressure times area. As the element is in equilibrium, the total force upward equals to the total force downward. So the force upward is equal to pressure upward times area. Meanwhile, the total force downward equals to pressure downward times area plus the weight of this element. So we take these two and put it in one equation and we will get this equation. So weight here equals to mass times gravity, while mass we can express as volume times density. And again, this volume is made from area times height. So eventually we can express W equals to rho g A times dy, the density times gravity times area and times the height of the element. The whole equation is divided with A as we consider the area is the same. And finally, we will get this equation. The pressure difference between 2 points equals to the density times gravity and times the height. So what do we know from the equation from previous slide? The equation shows that under normal situation, we can consider that the gravity is the same. If we are using one type of liquid, we may also consider the density of the liquid is the same. So we can conclude that the pressure in a fluid at rest does not change with the horizontal direction in the same type of fluid. But as we go deeper into the fluid, with the increment in the height, pressure will also increase. This is because more fluid rests on deeper layers, and the effect of this extra weight on a deeper layer is balanced by an increase in pressure. Let's say if you had a container with a hole in it, and if it's true that the pressure increases with depth, then the water should flow out further the higher the water level. Or you could put several holes at different height and show how the water flow varies. From this experiment, we can see that the water flow further at greater depth. It shows that the pressure in the water increases with depth, more pressure at the bottom than at the top. So this explains why dam has thicker walls at the bottom. As we go deeper into the water, the pressure goes on increasing. So the thickness of the wall is made thicker and thicker to withstand the pressure. Okay, just now we saw examples on fluid. How about pressure due to gas? Actually, the variation of pressure with height is negligible for gases because of their low density. For example, the pressure in a tank containing a gas can be considered to be uniform since the weight of the gas is too small to make a significant difference. Also, the pressure in a room filled with air can be approximated as constant, which means any point in the room can be considered as the same pressure. However, if you go to an extreme height, for example the mountain top, the air pressure will decreases. When the air pressure is lower, you will get less air with each breath you take. At the top of Mountain Everest, the air pressure is 1/3 of what it is at the sea level. With air pressure so low, many people have trouble breathing and thinking. And that is the reason why many people breathe oxygen from tank as they climb high the mountain. The atmospheric pressure exists around us. One of the examples of its application is when someone used the straw to drink. When this person sucks through the straw, pressure in the straw becomes low. The atmospheric pressure outside, which is higher, will force the water into the straw. So let's say we have a container filled with liquid. So the pressure at a point within the container is equals to the weight of the liquid plus the atmospheric pressure which exerts on the surface of the water. If we want to measure the pressure at this point, this pressure equals to the weight of this liquid, the liquid above the point, plus the atmospheric pressure which acting upon the surface of this water. So now let's look at this example and try to understand more about pressure. Based on our equation just now, P equals to rho GH, pressure equals to density times gravity and times height, a pressure at the same elevation in the same type of liquid should have the same pressure regardless of the shape of the container. So here, point A, B, C, D, E, F, and G should have the same pressure, which is P, pressure, equals to the density of water times gravity and times H, the height from the surface of the water, plus the atmospheric pressure. Meanwhile, point I here will have more pressure as it lies deeper into the water than the other points, point A, B, C, D, E, F, and G. Even though it has the same elevation with point H, it is also different. It is because the density of the liquid in point H is different with the density of the liquid at point I. So to conclude, the pressure is the same at all points on a horizontal plane in a given fluid regardless of the geometry, provided that the points are interconnected by the same fluid. Atmospheric pressure is measured by a device called barometer. It is measured by inverting a mercury-filled tube into a mercury container that is open to the atmosphere. The pressure at a point B is equal to the atmospheric pressure because it is at the same elevation as the surface of the mercury that is open to the atmosphere, which is at point D. So this point B and D is interconnected with the same fluid, which is mercury. And the pressure at point C can be taken to be zero since there is only mercury vapor above it. And the pressure is very low relative to the atmospheric pressure. So here we can see that the weight of this part of mercury equals to the force due to the atmospheric pressure. So writing a force balance in the vertical direction gives this equation where rho equals to the density of the mercury, g is the local gravitational acceleration, and h is the height of mercury column above the free surface. As the area of the tube is the same, we can cancel it out and thus leave us with this equation. Note that the length and the cross-sectional area of the tube have no effect on the height of the fluid column of a barometer. Now, why do you think that we use mercury in barometer instead of using water? I will leave this question to you as your homework and we will discuss it in our next class. For a given temperature, the density of the air is lower at high altitudes and thus a given volume contains less air and less oxygen. So it is no surprise that we will be tired more easily and experience breathing problem at high altitudes. That is why you have to undergo special training if you want to climb high mountains such as Everest to develop more efficient lungs. Similarly, a 2.0 liter car will act like 1.7 liter car engine at 1,500 meter altitude because of the 15% drop in the pressure and thus 15% drop in the density of the air. The lower pressure and thus lower density also affects lift and drag. So airplanes need a longer runway at high altitudes to develop the required lift so that they can climb to very high altitudes for cruising in order to reduce drag and thus achieve better fuel efficiency. So based on previous equation, Pascal law states that a pressure applied to a fluid in a closed container is transmitted equally to every point of the fluid and the walls of the container. Look at this figure, pressure at point 1 equals to the pressure at point 2. This is because it is at the same elevation and it is interconnected by the same fluid. So from here, we understood that force applied by a fluid is proportional to the surface area, which means that two hydraulic cylinders of different areas could be connected, and the larger could be used to exert a proportionally greater force than that applied to the smaller. This has been the source of many inventions that are a part of our life. For example, hydraulic brakes and lift. And this is what enables us to lift a car easily by one arm by using a hydraulic car jack. We noticed that from previous equation, P equals to rho GH, and elevation change in H at a fluid at rest will affect the pressure, which suggests that a fluid column can be used to measure pressure differences. A device based on this principle is called manometer, and it is commonly used to measure small to moderate pressure differences. Many engineering problems and some manometers involve multiple immiscible fluids of different density. For example here, fluid 1, fluid 2, and fluid 3. They are stacked on top of each other. Such systems can be analyzed easily by remembering these 3 points. The first point is the pressure change across a fluid column of height h is P equals to rho GH. Pressure equals to the density of this fluid times gravity and times height of the fluid. Second, the pressure increases downward in a given fluid and decreases upward. So as we go deeper into the fluid container, the pressure will increase. Number 3, the 2 points at the same elevation in a continuous fluid at rest are the same pressure. For example, you have 2 points that are on the same height in the same fluid will have the same pressure. So in Pascal law, we understand that we can jump from one point to the next point in the same elevation without worrying that pressure change as long as we stay in the same continuous fluid and the fluid is at rest. When the pressure at any point can be determined by starting with a point of known pressure and adding or subtracting the ρgh terms as we advance towards to the point of interest. For example, we want to know the pressure at the bottom of this tank or P1. So we start at free surface here where the pressure is equal to atmospheric pressure. So moving downward, we will plus the pressure from fluid 1. So P1 equals to the density of fluid 1 times gravity times height 1. Then we go downward again towards to point 1, we add fluid 2. Pressure at fluid 2 equals to density of fluid 2 times gravity times height of the fluid 2. And then we go downward again, so we have to add the pressure due to fluid 3. Pressure of fluid 3 equals to density of fluid 3 times gravity times height of fluid 3. Then settling at point of interest, which is at the bottom of this container, point 1. This equation also means that pressure at point 1 is due to the atmospheric pressure plus pressure from fluid 1 plus pressure from fluid 2 plus pressure from fluid 3. Consider the manometer as shown here that is used to measure the pressure in the tank. Since the density of the gas is small, we can consider that the pressure anywhere in the tank and at position 1 is the same. Furthermore, pressure at point 1 and point 2 is also the same, as it has the same level of height and it is interconnected by the same liquid. So P1 equals to P2. The differential fluid column of height H is in static equilibrium and it is open to the atmosphere. Then the pressure at point 2 here is determined directly from this equation. P2 equals to the atmospheric pressure plus the density of this fluid times gravity times H, the height of this column. Note that the cross-sectional area of the tube has no effect on the differential height H, and it is also to the pressure exerted by the fluid. However, the diameter of the tube should be large enough to ensure that the surface tension effect and the capillary rise is negligible. So here we can measure pressure at point 1 equals to pressure at point 2, and point 2 equals to atmospheric pressure plus the density of this fluid times gravity times height of this column. To review, any 2 points at the same elevation in a continuous mass of the same static fluid will have the same pressure. For example here, P1, the pressure at P1 equals to the pressure in here. This is because it is at the same elevation and it is interconnected by the same fluid. Meanwhile, this pressure here is equals to the atmospheric pressure plus pressure due to this fluid equals to the density of this fluid times gravity times height of this fluid. So manometers are often used to measure pressure drops across a horizontal flow section between two specified points due to the presence of devices such as valve or heat exchanger and any resistance to flow. This is done by connecting two legs of the manometer to these 2 points as shown in this figure, point 1 and point 2. So this is the flow section that we want to measure the pressure drop. The working fluid can be either gas or liquid whose density is ρ1. This is the working fluid. And the density of the manometer is ρ2 and the differential fluid height is h. The two fluid must be immiscible and ρ2, the density of fluid 2, must be greater than the density of fluid 1, the working fluid. A relation for pressure difference from P1 equals to P2 can be obtained by starting at point 1 with P1 moving along with the tube, adding or subtracting the ρgh terms until we reach to point 2. Settling, the result equals to P2. For example, here we start at P1, pressure at point 1. As we going down here, we plus the ρgh of this fluid, which means the density of fluid 1 times gravity times height. So height here is from here to here, A plus H. We are here now, so we can jump to the point B as it is at the same height and it is interconnected by the same fluid, which is the density of fluid 2. So from here, we going up, we have to minus the density of fluid 2 times gravity times height here, H. And finally, in order to go to point 2, we have to go upward again. We have to minus with the density of this fluid. So density of fluid 1 times gravity times the height, which is A here, equals to the point of interest, point 2. So note that we jump from A and B and ignore the part underneath since the pressure at both points is the same. We simplify this equation, we will get the equation here. So the difference between point 1 and point 2 equals to the density difference between liquid 2 and liquid 1 times gravity times height. So now let us try a simple YouTube manometer. So we want to find the pressure difference between point 1 and point 2. First, equating the pressure at level X and X dash. Pressure at the same level in a continuous body is equal. So X equal to X dash. This is because it is interconnected by the same fluid and it is at the same level of height. So Px here, pressure at point X equals to pressure at point 1 plus the rho GH of this fluid column. So the density of this fluid times gravity times the height of this column, which is A plus H. Then you will be going to get the pressure at point X. So now we move to pressure at the right hand side, Px dash. Px dash here equals to pressure at point 2. We're going down, so we add the rho GH of this fluid, the density of this fluid times gravity times H of this fluid, which is here is A, and we're going down again, so we have to add the rho GH of this fluid. So it's the density of this fluid times gravity times H here, the height of this fluid column. Then you will get the pressure at point X dash. So as we know, pressure at point X equals to pressure at point X dash. We take both equations here and put it in one equation. Then you can simplify this equation. Finally, you will get the difference of the pressure at point 1 and point 2 is the density of fluid 2 times gravity times height minus the density of fluid 1 times gravity times height A here. From the previous slide, we know that pressure at any point can be determined by starting with a point of known pressure and adding or subtracting rho GH terms as we advance towards to the point of interest. So here, we will make pressure at point 1 as the known pressure and pressure at point 2 as point of interest. We can start here. P1, pressure at point 1, as we going down, we have to add the rho GH here. So the density of fluid 1 times gravity plus A and H, which is the height of this column. Now we are here. Since the pressure here is equals to here, we can move forward to point 2, which is our point of interest. So from here, we're going up. We have to subtract this column, the density of fluid 2 times gravity times H here. And then we go up again, we have to minus this fluid column. So the density of fluid 1 times gravity times the height of this column, which is A, equals to the point of interest P2. We simplified this equation, we will get the same answer just like before. So now we have two ways of solving this problem. What if the U-tube manometer is inverted? Again, we can use the same method as we learned just now. So here, Px equals to Px dash because it is interconnected by the same liquid and it is at the same elevation of height. Px equals to pressure at point 1 minus the rho GH of this column. H here is A plus H. So this is your first equation, the pressure at point X. For the right hand side here, Px dash, so here again, we start from here, P2, pressure at point 2, as we go up, minus the liquid density of this column, rho times gravity times height of this column, which is A. We go up again, minus this column, which is the density of liquid 2 times gravity times H. Since the pressure at point X and pressure at point X dash is the same, we take these two equations and put it in one equation. Then you will get pressure difference between point 1 and point 2 equals to density of fluid number 1 times gravity times H, the height of this column. So we will see you again next week. Please do all the exercises given and we will discuss in the next class. Thank you.